Good afternoon, everyone, and welcome back. So our next speaker today is Cristian Perez from Toyota Connected Europe. His talk title is High-Octane Streaming, Managing Connected Car Data Flows at Toyota Connected Europe. So Cristian Perez is the data engineering lead at Toyota Connected Europe, driving data initiatives that power connected car technologies. With over 10 years of industry experience, he combines technical expertise and data insight, making him a sought-after speaker on data engineering and cloud solutions. With a talk titled High-Octane Streaming, please welcome Cristian Perez.
Thank you. Thank you. Thank you, Patricia. Hopefully you can hear that okay. That's good. So I'm not sure I'm going to be able to live up to those expectations in this talk. But the one thing that I'm going to mention is we're going to try to keep this a bit more light. I think that it's already 2 p.m. People already had a few beers. So feel free to sit back, relax, and try to take it all in. This talk is a technical practitioner talk, but we're going to start right from the beginning. So we're really going to go and zoom in, if you can imagine it, right from a satellite down to really a microscope of what it is that we do from a data engineering perspective at Toyota Connected. And I think, Patricia, you mentioned Toyota Connected quite a few times, so hopefully you know where I work. And we can start with that. I'm the data engineering lead at Toyota Connected Europe, specifically for the ingestion team. So the ingestion team actually does a really important piece of work, which is capturing data from every single Toyota and Lexus vehicle in Europe, and that sounds really fancy, but that is capable of actually transmitting data, okay? So the number of vehicles where we capture data is perhaps not as large as we would like it to be. But we're still talking about a couple of million vehicles that are on the road. And ingesting data from those vehicles is no easy feat, but we're going to get into that. We're going to get a view in terms of what that looks like and what are some of the complexities and problems that we actually face in order to ingest the data and make it useful for the customer. Along that, we're going to start with connected car. And the idea of connected car is actually quite foreign to a lot of people. And it goes way beyond just you plugging in your vehicle into a wall socket to charge it if it's an electric car. Connected car really is about actually taking that car that you drive and connecting it with the outside world. And basically being able to extract really useful features and analytics out of that vehicle. And this is a reality we have today. So if you drive a car that is 2018 or newer, at least a Toyota, this type of technology already resides within your vehicle, which is really important. But what technology? What does it do? And what is the problem that we're actually solving here? So in order to be able to understand that, we got to really go back to the beginning. So how is it that we got to a point where we require our cars to be connected at all? And there's no better way to try to understand that than to really go back in history and try to understand what is the history of cars. And of course, I'm representing Toyota, so I'll give you a very Toyota-centric history of cars. So hopefully you don't mind that bit. But we're going to go back right to the beginning. So this is 1936. There were many other cars that were actually invented in the 1800s. In fact, the first car that you could denominate a car actually worked with steam, and that was in the 17th century. But we're not going to talk about that. That's perhaps a bit too far back. So 1936 is the first Toyota car. Anybody knows what the actual model of that car was? The name? It's a very inventive name. Cool. One? Yeah, it's pretty close, actually. So the prototype was called an A1, okay? But the actual model was called Toyota AA. Quite a couple hundred of these vehicles were made. And you can actually see the correlation of this vehicle with American cars because they were heavily influenced by what was happening in the US around the car manufacturing bit. What a beautiful vehicle. Look at this. Look at this very demure, right? So what we have here is a proper vehicle. We had kind of fast forward from the stage where vehicles would need things like oil lamps to actually go in front and give you some light. And at this point, we had also fast forward through a technology of cranking your vehicle. So you have to crank it in order to be able to start it. But this was the first. This is what that vehicle actually looks like today in a museum. There was one that was found actually in Russia that had been used as a cabbie and then disposed of, and it's been rescued since then. But these vehicles were largely mechanic. They use an electric engine starter, so no more cranking, which is a fabulous feature to have in 1936. And they had a basic lighting system. So what that meant is that you didn't have to put oil in your lamps to be able to continue driving on the road. Furthermore, there was a battery in this vehicle. So what that meant is that we were actually introducing some sort of, electricity into the equation, and we were trying to connect the car in the inside. And that is really important, and that is not what connected car actually is, but it's perhaps the first version of what connected car, was going to be. Really important, most components actually acted mostly independently. So if you think about what was happening with the engine or the battery or the lighting system, they're quite independent. And if they had to be connected to each other, they would have this thing called direct wiring, which is exactly what the name implies. There's a wire running from one place to the other. So that's the beginning. What we had next in the 1950s was actually quite revolutionary. One of the earliest problems that we had when it came to cars was the ability to actually inject fuel into the engine. So if you may know by now that when it comes to powering an engine, you have to have the right mix of air and fuel. And the way in which we can manage that prior to electronics being in the picture was quite manual and difficult, and usually not consistent. Neither would it respond to external factors like the way that you're driving. So that's when the first electronic control unit was actually introduced. This is back in the 1950s. What is an electronic control unit? Well, it's essentially a small computer, if we have to keep things simple. And this electronic control unit, really, in today's cars, we have hundreds of them in one particular vehicle, but is very much dedicated to one thing and one thing only. So this electronic control unit is basically the computer that may drive your air conditioning, or that may actually be responsible for things like lowering your window, or for detecting when you actually turn on your car. So very specific in terms of what they do, and this is something that is changing over time. But ultimately, at its core, it does two things, and those are the two things at the bottom there. So it acts as a sensor, so it's sensing that something is happening, and then it's able to trigger an actuator, which is just a way of saying it's going to go and do something else with a different component. So when you put the key into your vehicle, I mean, right now, maybe you're pressing a button, but if you're pressing a button in your vehicle, then there is an ECU that is actually listening to that. So it senses that you've pressed that button, and then it's going to go and start the engine ignition process. And that is the actuator. And this is important because we are now introducing different devices into the vehicle that need to be able to interact with each other. But we're stuck in what we were just talking about back in the 1930s, this direct wiring, and we were not really bringing all those together. So what happened next? Next, we had a really, really important piece of technology, which is the anti-lock braking system, or so-called ABS. Very well misunderstood by many people who don't actually understand why you even have a button to deactivate it, right? But this particular feature, while it's complicated in the way in which is managed inside of the vehicle, can really be summarized by something like this. Okay, so here we have two dogs. We have Welly and Joe. Welly has his ABS on, okay, and Joe has his ABS off. And Welly here on the left is actually using what I call a quadruple paw action in order to stop his owner from bringing him into the water, whereas Joe is just not doing that. And in the picture, perhaps not as realistic as we would want it to be, because Welly should have stopped before Joe, but he has another force acting up on his head, which then doesn't make it count. But this is really what ABS is, right? Is the ability for the vehicle to literally stop in a controlled way, and you're applying that braking in an intermittent way. Really complex process that requires serious computing power. It requires understanding of the car as to how fast you are, what is the braking that you require, and how harsh is your braking allowed to be. So ABS, really important one. We'll keep moving and fast forward to the 1980s, fabulous decade, right? I was born in the 1980s, so I consider it a fabulous decade. But another great thing that happened in the 1980s was onboard diagnostics. So it doesn't sound nearly as exciting, but one thing that cars do really, really well since the beginning of time is breaking down, okay? That is the one thing that cars are really good at, and because of that particular issue, onboard diagnostics are really important. We need to find a way to know what's wrong with my vehicle, okay? Many moving pieces. You've got technicians that are trying to figure out what's the problem that you have. So this first version of onboard diagnostics was really, really good and really advanced and actually looked something like this, okay? And this is a picture of one of the first Cadillacs in the market. And as you can tell, is an aircon, climate control unit, really. And it did a lot more than climate control. If this car had an issue, it would actually display a numerical code in that air conditioning unit. So the technician would be able to press a couple of buttons, and then they will get a 3-number code that would tell them what was actually wrong with the vehicle. Amazing. Air conditioning, how far did it go? So those codes are actually referred to in the industry today as DTCs, or diagnostic trouble codes. And they survive to today. They're actually critical to the way in which we diagnose vehicles today, which is why this advance was very relevant. And last but not least, 1991, so I was 2 years old, so not as great of a year, but the one thing that did happen was the creation of the CAN bus. And the CAN bus stands for Controller Area Network. And what is this mysterious CAN bus? This CAN bus is what brings connected technology into the modern era. Because what it did is it took all of those different electronic control units that vehicles had, and it put them on the same wire. So in technical terms, they formed a network, okay? And this network was actually really good because the wiring of that network was quite resilient to the elements, because vehicles are in mud, water, snow, and if you want them to be able to communicate with each other, you need a network that can actually support that. So that's what the CAN bus is, and it is quite complicated, but with the help of AI, I worked on a particular diagram that I think that is quite complex, but it will bring the CAN bus to light. So that's what was happening with those ECUs, okay? We've got many different ECUs sitting in the wonderful world of vehicles, and they're actually coming together. And the good thing is that even if one of those ECUs go down, there's no issue for the network. So it's a network that doesn't depend on a particular node going down. It's actually a bus, for those of you who are really techie, but it's specifically a bus that is able to prioritize messages based on something called a data ID, which is basically an identifier in that network. So that's what we had, and this really starts this new era of the car being connected inside. So we're still not talking about connected car as such, but we're talking about the connection that is taking place inside of the vehicle. Those computers were no longer isolated, and we really were ready for the next step. And the good thing is that everything was fixed, onboard diagnostics was resolved, and then car manufacturers never had to worry about that, neither customers in terms of their vehicles breaking down. Which is obviously not true, because you still get to experience things like this, right? And we obviously, this picture is actually from a Prius, it's a Toyota Prius, and what you can see here is that there is an issue with, obviously, the engine, along with a couple of more warnings sitting there. And that is the second component, by the way, of onboard diagnostics. So we talked about diagnostic trouble code, which was that 3-digit code, and now we're talking about something called a warning. And the warning is exactly what you see there. The warning doesn't tend to tell you much about the issue, And then what really nails it down is the DTC, or the diagnostic trouble code. It's sort of like, you may be hungry because you haven't eaten, or you may be hungry because maybe you had an argument with your partner before, right? So the diagnostic trouble code matters when it comes to the warning signs that you're being given. So prior to connected car, how did we know what the actual diagnostic trouble code was here? The way in which we found out was by this wonderful machine, which some of you may be familiar with, right? So it's a diagnostic code reader, and it does exactly what it says on the tin, okay? You take that connector to a port in your vehicle, which exists today, by the way, because it's the law in the EU to actually, it was an EU law initially, but worldwide it's been adopted, where you actually are required to have the same port in every vehicle. Kind of like USB-C for iPhone, but the version of the cars back in the 90s, okay? And you could plug this in, and then you would find out what the actual code was, what was the diagnostic trouble code, and the mechanic would do that. But this still meant that you had to go to the mechanic whenever you got that warning. You had to go to the mechanic, and you had to take your car there, and then he would have to plug in this machine. And after plugging this machine, he usually would have a reference book. And in this reference book, he would look at the meaning of that and then figure it out. Very often, mechanics just didn't care. They're like, I'll tell you what's wrong with this vehicle, right? And they will go in there and try to fix it. Regardless of what was right or wrong at that stage, it was still a very difficult way of dealing with cars and providing a really good customer experience. So this is where we actually entered the connected car era. So we figure we're in the 2000s. We've got all of these ECUs talking to each other. We've got these warnings and codes. The internet is here. So what is the natural technical thing to do? Well, it is to put a phone on your vehicle, right? And not quite literally like this, but what we decided to do at Toyota was actually place this module called the DCM, or the Data Communications Module. And what this module is basically a network gateway that allows the vehicle to communicate with the outside world. And that module contains a SIM card. So if you're driving a car that is newer, 9 times out of 10, I'll tell you that there is a SIM card in there that is capturing data of the vehicle. Now, that sounds really scary, so don't worry. Privacy and consent are the pinnacle of this. So this is post-GDPR. If you are driving a vehicle that has this type of technology, you're very likely doing something like paying for a plan that actually allows you to enjoy that type of feature. And you would have to explicitly consent. I can't speak for other manufacturers because they're not that good. But when it comes to Toyota, we will explicitly capture your consent and your privacy settings before we do any sort of data capture of this type. Now, here's where things get interesting, and we're going to dive into a bit more of the technical portion of the talk. And don't worry, we'll still use some analogies, so if you're not like mega technical, you should still be able to follow. But what we're going to do is we're going to try to figure out how it is that we in Toyota Connected were able to accomplish this, right? Because our goal was to get to a point where those warnings and those diagnostic trouble codes would be presented in a friendly way, not with a scary number, to the customer. And if the customer paid for the plan, we want the technician that the customer has chosen to also have access to that data. So guess what? When your vehicle has an issue and a warning light comes on, the experience that we want to create is that at the same time, you have chosen a dealership that you prefer, and maybe an appointment will be made for you automatically. And all you will get, along with your warning, would be a confirmation of what appointment would work best for you to actually take your vehicle. And you wouldn't have to talk to them because they already know what the actual code is. By the way, not that I'm selling Toyota products, but we do have that feature today, okay? So, but we're gonna talk about how we actually were able to achieve that. So, we're gonna jump into the weeds of things, and here's where we're gonna cover some of the technical challenges that we actually had from a data engineering perspective to be able to consume this data and do exactly what we do today in terms of that particular service, which is just one of the many services we offer, but it was still quite challenging to actually accomplish. So from a high level, this is kind of what it looked like. This is the flow. So you've got a connected vehicle or a data communications module, and then next you've got the mobile operator, which is in the middle, obviously. So here we're talking about the Orange, Vodafones of the world. We have contracts with them across Europe, at least. And what we do is we capture data from those mobile operators over to us. So you can think of us as that data center. And we have to deal with that data somehow, and we have to convert the data and make it usable so the customer can actually benefit for that data, meaning that maybe the technician now knows exactly what the problem with your car is. So you don't have to try to explain what is the sound that your car makes. You remember that, right? Tock, tock, tock. How do we accomplish this? This is the engineering challenge from a data perspective. How do we consume data from millions of vehicles that are making millions of trips every single day? And how do we make sure that that data is actually arriving in the way that it is supposed to, those warnings and those DTCs? This was our first take to it. So we used two pieces of technology. We thought this was a match made in heaven. The rest of the engineers would highly disagree with that. But the technology that we ended up using for our vehicles to transmit data was this protocol called MQTT. Okay, so this stands for Messaging Queue Telemetry Transport, and basically what that is, if you've ever heard of we had the hype of the Internet of Things, which is nowhere close to the AI hype. And unfortunately, I don't have an AI slide, but I will try to make it up as I go. But MQTT really is this lightweight framework that allows you to send data in batches over the network. And it supports quite a lot of throughput as far as data is concerned. Not really big sizes, but very frequent communication. And then we had to be able to ingest that MQTT data. So how did we do it? Well, initially we did what every sane engineer would do at that time, and we actually created a service that would subscribe to those MQTT topics. So that's how MQTT kind of works. It kind of categorizes your data, and it tells you, hey, this data is ready, you can consume it from this topic. And we started consuming that, and we were like, okay, we gotta get this pretty quickly, because the experience that we want is that the customer knows literally within a minute that a warning has been fired. So even if it's your partner that is driving the vehicle and they get the warning, you will also find out if you have the app, right? I mean, that was not specifically the intent, but right? But then that's kind of the experience that we were after. So the way in which we wanted to accomplish this was by using a messaging bus, and in this case, it was Kafka. If you're familiar with it, who is familiar with Kafka here? Okay, so we've got about half the room, which is good. So we basically wanted to use Kafka as the messaging step between our ingestion and the app. But then we ran into a bit of an issue, because one of the engineers in the R&D hardware team came up with this idea. He said, listen, warnings and DTCs are not enough for a technician to decide what is the problem. We need to give context to that technician. So we need to know what was happening before that warning was fired and what was happening after that warning was fired. So if you're driving, 150 miles an hour down the motorway and then your transmission blew up, well, we kind of know what happened, right? We know what was the rationale behind it. So we came up with this idea of taking snapshots of the state of the vehicle before the warning got fired and after. And these snapshots were complete. So we take a snapshot of every single ECU for a period of, say, 60 seconds. And then we're continuously doing that, and whenever there is a warning, then we'll send the previous 60 seconds, and then we'll send the following 60 seconds as contextual data. This obviously represented a problem. This amount of contextual data is far too much. And Kafka, while amazing in terms of speed and being a very lightweight kind of framework, really started to struggle when it came to being able to consume these data. So we were faced with these horrible exceptions where Kafka would just simply refuse to accept the reality that a big snapshot had been created for it. So this made us really sad. And we knew that we actually had to go ahead and change the way in which we had architect our services. So we did the right thing, right? And we said, design patterns are the way to go, because when in doubt, just look at some guy 30 years ago, and he's already said the right thing. So design patterns are always good, and we found one that actually specifically addressed this. And who did it was none other than Gregor Hope in 2003 in his amazing book, Enterprise Integrations. And the pattern that he described was this thing called the claim check pattern. All right, just hang on with me, okay? So if you're not following, we'll explain it all. So the claim check pattern is really simple. It kind of mimics what you do at the airport. So at the airport, you have some really big bag if you can afford the ticket for the checked baggage. But you go there and you have your checked baggage, right? And you bring it in, and they give you a ticket. They give you a claim check. And that claim check is what you're going to put in your pocket. And when you arrive at your destination, what do? You present your claim check, and then you get your baggage. That's the solution we came up with for this really big size problem. So we would consume the data from the vehicle, and we would store that data, not in Kafka, but actually in S3, so in actual state. And then the only thing that we would send in Kafka would be the claim check. And then we got really smart, and we're like, not just the claim check, but we'll send a few other data points so other services downstream can kind of make sense of it. And that's how our architecture ended up changing to this. So what we ended up doing was consuming that data, saving it, sending that claim check over, and then the next service, based on that claim check, would decide if it was worthwhile consuming that data or not. What that really meant is, for example, if your warning or your diagnostic trouble code was triggered while your vehicle was in service, then of course the customer doesn't want to know that, right? That would be useless if you took it to the dealership and you got a bunch of warnings on your phone about it. So one of the things that this data enricher would do is try to make sense of that and say, okay, do I actually need to send this warning? And is the actual vehicle in service? If it's not, then let's not worry about it, and let's just drop that. But if I need to worry about it, then I'm going to go ahead and fetch that really big file using this claim check pattern. Now, we thought that we had solved all the issues, right? And I don't know if anybody has heard of the expression shaving yaks. It's a few. Okay. There's a really good Malcolm in the Middle episode about it. But shaving yaks basically mean that you just get carried away with many tasks, right? So if you say you want to go and take a shower, then you go to the shower and you try to turn on the light, and then the light doesn't work, and now you look for a replacement for your light, and then you go, and then you figure out that the drawer is not actually aligned. And then you try to fix it. That's shaving yaks, okay? And in software engineering, this actually happens quite a lot. And it happened to us while we were working on this particular issue, because we had yet another streaming problem once we were able to solve the size issue. That next problem really is, what is the streaming engine that we were going to use in order to actually process all of this data coming from vehicles? We're talking about millions and millions of trips happening every day. So this thing needs to be like really high throughput. And now we have introduced this S3 bucket at the bottom that contains really big files, which are those snapshots that we talked about. So when we tried to do it with Kafka, we started to notice that things were really slow. Like really slow, okay? Couldn't understand why. And then some engineer said, listen, there's this other thing called Apache Flink. Maybe we should take a look at it. We started to take a look at it, and we also got the same result. And then we kind of moved into this POC world. By the way, don't get scared about this. This is just a very simple Kafka Streams application on the left and a Flink application on the right. And it's not the actual real code, all right? But what it's doing is, I believe we ended up uppercasing every line on a particular file. But this code actually looks very similar, okay? So you've got We're from line to 5 to 13. We're kind of setting up the context. We're opening a file. We're splitting it. Very common thing to do in any sort of data engineering science kind of role. And then trying to load the file. And it was still performing really, really poorly. We couldn't understand why. So in terms of the investigation, we kind of dove in, and of course, just like everything in software engineering, when in doubt in an issue, blame the DevOps team or the cloud team, okay? And I wouldn't call it the DevOps team, but the cloud team. And that's what we did, and it turns out that we were right. So, okay. As it turns out, Flink needed a lot more than just code. It needs proper infrastructure to live, right? And so does Kafka in many ways. And what we found out with Kafka is that we had this issue around parallelism. So if you forget about the topic that is in the middle on the left, right, and you have this big file in Kafka streams at the top, if you try to get Kafka to just read a file directly, it will only do it in one instance, okay? So even if you have 20 different services deployed, only one of them will be actually working on reading that file. Not good, right? It will fall over, the file is too big, it'll explode, people will be unhappy. If you use this actual pattern, which is you actually put the file into the topic, and then from the topic, you can actually put it right into the Kafka Stream services, then things improve because you can actually parallelize the entire process of loading that file. But the problem is that then you really have to spend a lot of time thinking about how you structure that topic. So if you've worked with Kafka before, you may be familiar with partitions, which are basically just really small slices in that Kafka topic. You have to define how many partitions you want. You have to anticipate how many consumers you're going to have because they need to match that number of partitions to actually be properly used. And in addition to that, you need to think about how your data is being partitioned across that topic. So you're getting into keying concerns, what algorithm am I going to use and what am I going to call it? It gets complicated, okay? And we just wanted the that snapshot of data, contextual data, to be able to go to the customer, well, and mostly the technician. So it was complex. We kind of made it work, but we didn't like the solution. And then what we tried next was Flink. So Flink was actually really good because it gives you some of these features out of the box. So Flink has this job manager, which is essentially a leader in the cluster. And you've got these workers, which are other computers that are listening to that leader. And that leader already has a set of instructions where it can say, oh, I've got 3 workers. I've got this big file. I'm going to split it into 3. And I'm going to wait, and I'm going to split it in a way in which it makes sense. And that level of automated job management makes it really, really effective for actually dealing with big files. Don't take me wrong, we still love Kafka, okay? And there is a special place in our heart for it. But when it comes to Flink, it did this one thing really well, which is the ability of interacting with really big objects in a stream under pressure, okay? That's beautiful. If you can work under pressure, that's exactly what you want. So that's what we ended up doing. It also had this thing called checkpoints, which is basically the ability of Flink to say, hey, I've worked until here, and I'm going to just save it, okay? And if I fall apart, I can just look at the last checkpoint, and I will continue from there, which Kafka really doesn't have. If Kafka falls apart, if your Kafka Streams application falls apart, the whole state of that application, once it comes back up, it will need to be reconstructed on the fly. So that's really good for small stateless applications, but if you're consuming all of this snapshot data, it's just a no-go. And if you've been lost during this last part of the presentation, then you can think about what we did in this way, right? So you've got, in one side you have Kafka, which you kind of have a human teller and a bunch of people trying to go into an underground station. I did ask DALL-E to create a queue of people going into the underground, but they're somehow in the station already. But we'll leave that aside, okay? But yes, this is just a human actually going one by one, right? Whereas what Flink is really doing is if you were able to do the same, but replicate it with an automated way so people could actually flow, in this case, people representing little chunks of that big file. So with that said, we move into the conclusions. So the first one is obviously the evolution of vehicles has been insane, okay? Remember the cranking, right? We have moved away quite a bit from there. Diagnostic data was just the beginning, so we are actually moving into many other domains. And connected car technology is definitely here. In fact, hopefully you heard about it before, because now connected car technology is almost considered old, okay? And now the new thing is this thing called software-defined vehicles, where vehicles actually act like just really big smartphones with wheels. And you can just deploy apps into it, and you'll be able to deploy apps that maybe interact with all of the vehicle, not just for your entertainment. So that's kind of where we're going. Autonomous vehicles, of course, how could we not mention it? We won't say that T name here, but there's plenty of other manufacturers, moving forward with this type of technology and pushing kind of the next frontier. So if I can leave you with just one thing, is hopefully the understanding that these things that you own, called cars, we really just get to use for 5% of the time that we have them. The other 95% are kind of sitting there. And that's not okay. There are things that we'll be able to do to change that future. And I think that we're in a really pivotal moment to be able to do that. So hopefully you walk out excited about what your car can do the next time that you get in, and trying to spot what's happening with the car and how you can interact with it, with your app and everything else. Thank you very much.
Hi, thank you very much. Very interesting. We loved it. I have a couple of questions. The first one is about Kafka. I've used Kafka in past and nuts. I don't know whether you know it. It's an open source version that's not Java-based. Very cool too. A problem we had was this. Imagine that you have a lot of packets, and for some reason you start losing packets. What nuts used to do, something also Kafka can do, is to store temporarily those packets and then replay back. But this creates downstream issues, right? Because then you have an increase, a load increase somewhere else in your flow. First question is this. Does this happen to you, and how you tackle that? The second question is about the message. In one of your slides, I saw they are serialized. So you cannot really inspect them. That's a downside. It's not a massive message. I saw the limit of 10 megabytes. Do you need to inspect them on the fly? Some heuristics, a bit of data science, these kind of things? Thank you.
Yeah, no, not a problem. So let me first tackle your second question. So in terms of serialization, what I've shown is a very, very simplified view of many different types of cars and devices that we support. So there are some of the newer devices use serialization patterns that are much more advanced. So some of them may be using really simple stuff like just plain JSON, and then we can really inspect them on the fly, and they're quite big and human readable. But some other serialization types, we may be thinking about things like protobuf, for example, and using gRPC connectivity. So in those cases, we still serialize or deserialize to compress it. But the file sizes that we're dealing with newer cars are humongous. So some of the file sizes actually reach 200 or 250 megabytes from one single vehicle. So the 10 megabytes was perhaps making more reference to the earlier versions that we were dealing with when this architecture was coming about. And as far as your first question, you mentioned what is it that we do if Kafka, did we ever try to have Kafka hold state itself? Yes. No, I think that's a very fair question. So we did. So we made use of Kafka streams. As you may know, Kafka uses RocksDB under the hood, and then you can actually create things like K-tables and K-streams. And they were actually quite useful, and we probably could have gotten away with it. But what we found is, because we have hundreds of services deployed, whenever those services would fall apart for whatever reason, they would have to rebuild their state inside and actually basically go back to the topics that they were producing into and try to reconstruct the state. And as they were trying to reconstruct the state, they were just taking too long. So then we were really dealing with serious back pressure issues. Not this type, but the Kafka type, right? And with that, we just it was not something that we could tolerate given our use case. Yeah, that's it. Cool. Yeah.
Thank you for the interesting talk. Yeah, really fascinating topic here, streaming data. So the question that I have here is, yeah, you have a lot of data there, but I wonder, like, you guys also working on some project related to predictive maintenance, anomaly detection. Can you, if you work on those, can you talk a bit more on those?
Yeah, we definitely do. So in terms of anomaly detection, do you mean anomalies from like what we expect from the vehicle, or the vehicle has an issue that we want to proactively address?
Yeah. Before
okay.
Breakdown,
yeah.
You can detect it in advance and something instead of wait until
Fair enough. So no, I think that's a really good question. So what are we doing about anomaly detection and dealing with this data? We do have many programs, and we've deployed a number of different machine learning models that are actually very much focused on that. So we've got 2 generations of vehicles that we look at. We've got the older generation, where all we're capturing is essentially all the stuff or the history that you have as a driver, and then we do that with everyone who's given us their consent to do that. And then we're able to create a predictive model where we say, okay, given this set of factors, we think that maybe your tires are running flat, or that your battery will have an issue, or whatever else. So we do have those type of models. In terms of newer vehicles, it's a bit more advanced. So there is a lot more stuff happening in the edge, which is really good. So happening on the device itself. I don't think I can give a whole lot of details behind it, as you can imagine, but yeah, there's some interesting stuff happening there. Definitely. We've got it. We've got it from a data science perspective. The potential is huge, right? Because we could be working on those models. That's right. Yeah, no problem. More questions? Yes?
Yeah, thank you very much for the session. So I just wanted to ask regarding the DTC, which is the diagnostic trouble code. Is it the same across all OEMs? OEMs means original equipment manufacturer.
Yeah.
Is it across all OEMs?
It's a really good question. So remember we talked about that law that came out of the EU, right? So the push around standardization was not just the port, but was actually those codes as well. So there's a number of codes. There's a number of codes that are always the same across different vehicles, or the manufacturer is obliged to tell you what the code actually means. And then there are other DTCs that are not considered basic, not considered by this regulation, where you would actually, they're proprietary. So it's up to the manufacturer to figure it out. But yes, some of them are across the board, discoverable, and or the same, or the manufacturer just has to tell you what it means.
I'm asking because I work on it, so it's just very good to understand that it's not just my company, but across all board. Then one more question. Do you think it will replace DCM in the nearest future? I mean, the DTC?
Yeah, it's an interesting one. I think that there is a big push in the industry to really have this software-defined vehicle, and the software-defined vehicle will require some changes, perhaps not having a DCM. And I'm not talking about Toyota specifically, but perhaps for the industry in general. I think the future will probably have some more centralized, robust computer that lives in your vehicle that will be capable of doing things on the edge. Not saying that that's what we're doing at Toyota or anything like that, but it's what the industry is kind of moving towards. So I think that will definitely be a change that we can expect. Yeah, problem.
Hi, no, thank you so much for the presentation. One question that I've had is kind of like previously, so we know that, AI has been getting into kind of like drones, so Internet of Things. So with cars, the way that things are going, do you see the use of machine learning and AI more kind of in the cloud, taking data from the cars and the processing is down the cloud? Or do you think the trend is going towards more like in the car processing on the spot and then only sending alerts? I just want to kind of get your thoughts on that.
Yeah, no, I think that's a great question. I think, industry-wise and everywhere, right? I can't give a whole lot of details, but my personal view here is definitely we're moving more so towards the edge side of things. So we've been pretty heavy on the cloud in general. Now we're moving over to the edge. And because of autonomous vehicles and how fast they need to react, a lot of them do not have the luxury of sending their data to the cloud and just wait to see if I swerve or not, right? That would be really bad. So you have to do the processing in the vehicle, get it really, really fast, and I generally think that's the future because of that trend.
Yeah. Okay. Yeah, thank you. Yeah, so my question is, the car scanners, right? Do we really have models that sort of give you like a granular breakdown to the kind of fault you have? So take, for example, at times you scan and you get errors like, say, cylinder 1 faulty, right? Or cylinder 2 faulty. But of course, we know what the cylinder actually is in a car. But in some cases, like I've seen, it might not really be the cylinder. It could be components that fall under the cylinder, like maybe your spark plug or your ignition coil, whatever. But at least you're more than certain that it's that cylinder number that gets affected. So is there really any plans to sort of have an upgrade to the point where it doesn't just tell you cylinder 1 faulty, it rather tells you maybe it's the plug under a certain cylinder that is faulty? That's my first question. And for my second one, you did mention recent models, like when you have errors coming on your board, right? Like it automatically sends a signal to maybe a dealership and automatically books you for maybe a visit or something. So my question is, if it happens to be a fault that you can fix yourself, right? So maybe like, you're more than sure that maybe the ignition coil was not properly fixed, or it's been slacking, and all you just did was to just unplug and push back. Yeah. And that error becomes cleared. Yeah. So does it automatically send that signal to the dealership and cancels the appointment that has been booked in this case, or what exactly happens?
Where does it work? No, that's a really good question. So that service that we offer, where we send that data to the dealership, is a value-added service, which really means that you as a customer like actively pay for it. So the assumption is that if you're paying for that service, if you want to actually have that data collected and transmitted, regardless, we still give you the ability to choose that preference. So if for some reason you're paying for that service, but you still don't want to share the diagnostic data, which, admittedly, you probably want to review whether you need the service or not. But if you want to do that, you still have the control and the power to actually, shut off those alerts from going to the actual dealer. And in terms of repairing it yourself, I mean, it's a really long. I think it's a really long conversation. It probably merits its own presentation. Our stand at the moment really is, obviously we're there to help, so are the dealerships. So we offer that value-added service, but obviously customers are welcome to repair themselves. And if you choose not to share your data when you want to repair it yourself, then you don't need to. And to your first question, yes, we're trying to get really granular about these diagnostic trouble codes. Right now, they're just a big net, right? And they're getting more and more granular as time goes by. But ultimately, what you would want to get to is have a diagram of your vehicle, and instead of a number, it like highlights the part that is actually having an issue. And maybe you can just have that part order. I'm not talking about Toyota, but in general. But you can have that part order on your behalf right away, and then you can have it fitted somehow. So I think that is definitely the future, and we are getting much closer to that. But yeah, we're not there just yet.
Sounds like a sci-fi movie.
Like a sci-fi movie, exactly. One more question, all right?
Hi, left. Yeah.
Okay.
Thank you, very insightful. I just wanted to know, because today we talk more and more about AVs and safety in cars, and you get data with cloud computing and stuff like that. But I saw in recent research papers that edge computing is more and more considered with vehicles to process the data really near the road, and then have quick feedback and take actions in the car, so from the driver or just in an autonomous way. What's your perspective or maybe opinion for Toyota, or maybe more broadly in the future, how do you think this will be implemented? And also regarding V2XO, vehicle to everything, maybe vehicles could, maybe vehicles could communicate between them. How do you see this in the future?
Yeah, no, that's a really good question. So I'll speak from a personal standpoint rather than Toyota's, but I definitely see that migration happening from cloud to edge. And I think that's happening today for the reasons that you mentioned, whether it is autonomous driving or just really smart safety features that you can do that. The way in which you accomplish that usually is by, being able to do this thing called OTA, or over-the-air updates. And what that means is that we can push data actively to your vehicle, kind of like a software update on a phone, right? And we can push that data, and what we can do is we can get a machine learning model, train that model, push that data to your vehicle, and then on edge, you're just going to enjoy the outputs of that model. And that generally requires different hardware to be able to accomplish that, which is why I think that the trend will continue to have, better hardware in the vehicle, unless we have a crazy uptake in our ability to collect that data. But it's unlikely. I think what's happening right now is there's definitely a push to an edge. Toyota is certainly moving, I think, in that direction. Things might change in the future, but as I see it right now, I think edge computing is where it's at, and utilizing pre-trained machine learning models running on the edge is probably what we're likely to see in the next few years.
Thanks.
Yeah, no problem. All right.
Give Cristian a warm round of applause. Thank you.
Thank you very much. Thank you.